Hello everyone, I'm Adil and I will be presenting this work which deals with developing predictive models to capture the aggregate dynamics of large fleets of distributed energy resources. The focus of this work is on a device-driven DER control scheme called Packetized Energy Management. Distributed energy resources, for example electric water heaters, are flexible since their power consumption can be shifted in time. Aggregations of DERs can then be coordinated to act as virtual batteries and provide services to the grid such as peak load reduction or frequency regulation. In packetized energy management, DERs request to consume power from the grid for a short time interval which is called as a packet length. These requests are made according to a pre-designed probability of request curve. The PM coordinator can then decide which of these requests to accept depending upon the total power consumption of the fleet and the reference trajectory provided by an aggregator or a utility. DERs are also allowed to opt out of PEM if their energy state is low. That ensures quality of service. The objective of this work is then to develop a model that can capture the aggregate dynamics of the fleet in terms of a few key quantities such as state of charge. This model is called as virtual battery model. The virtual battery model, or VB for short, for thermostatically controlled loads such as electric water heaters consists of three states. The first state captures the dynamics of average state of charge of the fleet. The average state of charge of the fleet decreases as a result of heat loss through the lining of hot water tank. The average effect of end users consuming hot water from the tank is also captured. That results in a decrease in the average state of charge. Finally, the total number of DERs that are consuming power from the grid contribute to an increase in state of charge. The on-population dynamics are governed by the PEM system. In this case, the DERs whose requests to consume power are accepted are allowed to turn on for a short time, such as 3 minutes, and the DERs that have just finished consuming their energy packet transition to the off mode. Finally, the opt-out dynamics in PEM are captured that evolves depending upon the total number of DERs that have just opted out due to insufficient energy, or DERs that are opting into PEM after recovering their energy state. The proposed VB model has the benefit of capturing the aggregate dynamics of the PEM system in a few number of states as opposed to the population model or bin-based models. Bin models are more accurate than VB models but require a large number of states, which is not usually preferred for a predictive control formulation. Our simulations here show that the proposed VB model is suitable for prediction. For example, in this case, the fleet is tracking a reference signal that is well below the nominal power consumption that is required for a nominal operation of the fleet. This causes the fleet to discharge on average, and as you can see here, the VB model can capture this behavior. Similarly, we can also use the VB model to test trackability of different reference signals. In this plot, the fleet is tracking a sinusoidal signal around a nominal value. As we move from left to right, the amplitude of the sinusoidal signal is increasing, and the last plot here shows that the fleet, which consists of electric water heaters only, is unable to track the reference trajectories below zero. So we can use this model as a predictive tool to identify the regions that are not trackable by the fleet. To conclude, we have proposed a low-order virtual battery model that is suitable to predict the aggregate dynamics of a fleet of distributed energy resources operating under packetized energy management. This model can be used in optimal control formulations that takes as input a reference signal that may or may not be exactly trackable by the DERs. The objective of the optimal control problem is then to modify the input reference signal according to the capabilities of the PEM system. This modified reference can then be fed to the PEM coordinator. Also, the VB model is nonlinear in state and control input, but we have shown that it is strong locally observable. Finally, we are working on using this VB model to quantify flexibility as kilowatts per device, which is more suitable when providing services to the grid. Thank you for your attention.